The notes are going to be real short today. We're just going to go over power. So power is it's the rate at which work is done. So, if you're changing energy, if you're giving energy over time, that's what power is. It's how much energy you get over time. And so, and it is what you're used to when you think about like electric power. That's what power is. If something takes, 450 watts of power, then it's taking, 450 joules every second. So that's how much energy it's taking every second. So it's the amount of energy consumption over time. Okay. Sorry. So it has an equation. It's equal to work over time, which makes sense. It's the rate at which work is done, so it's work over time. But it has this other form. We can find this really easily because since work is basically force just times distance, assuming, they're in the same direction over time, well, that's force times this is velocity. So you kind of find this equation in that formula to begin with, but we need to know that work over time is equal to force times velocity, which is equal to power. So let's try a couple problems real quick. A box is pushed to the right with 60 newtons of force, 5 meters, 30 seconds. What is the power of the push force? Okay, well, if we have a box on the ground, we can assume many things. We have gravity with a normal force, but all we really care about is that there's a force forward that's pushing the box to the right, and then the box is actually moving to the right. Okay, which means that the angle between them is 0, because the angle between right and right is 0. Okay, and so if we want to find the work done by this force, we know it's equal to force times displacement times cosine theta, so it's equal to 60 times 5 times cosine of 0, which should be equal to 300 joules. Okay? And so if we want to find the power done, power is equal to work over time. And so all we have to do is plug in work over our time, which is 30 seconds, and so we get 10 watts. Pretty simple. The hard part here is really finding the work, okay? Or if we're going backwards, you need to know that we can use a given power to find work. If we're given power and time, we can solve for work, and then we can use that work going backwards to even maybe find the force or displacement, assuming, again, we're given everything else. Let's try a different one. Let's say a force of 4,000 newtons is required to keep a car traveling at 8 meters per second. How much work is done in 1 minute? Well, in this case, if we're given the force and we have this velocity, and we're talking about work done in time, we have all these equations. We should start associating them and thinking about, okay, I have a force, I have a velocity, I have work, and I have time. Or I'm looking for work, and I have time. Then I know there's an equation that relates them. We're starting to get to the point in this unit where the hard part is figuring out what kind of problem it is, like where do I go from here? And so it's really going to benefit you to start with your givens. And that's what the review is really going to be the practice for this. So whenever we do the review, it's really practice, okay, what kind of problem is this? In this case, if I write down all my givens, I see, okay, force, velocity, work, and time. I know what relates them. Work over time is equal to force times velocity. Okay, there's that power equation that relates all these. And so I know if I want to find my work, work divided by 60 is going to be equal to 4,000 times 8. And so it's going to be pretty easy to do. I can just multiply 4,000 times 8 and then multiply it by 60. And I get a pretty big number, 192,000. Joules of work. Power is not very complicated. It's a pretty simple equation. You just have to, again, I think the main complicated thing of this unit is work, using work effectively and using work with the work energy theorem, finding work and doing all that stuff. And so you need to get a lot of practice. If you didn't do the homeworks, I've had, this happens. I have people that just decide not to do certain homeworks. You have to do the work one and you have to do the work energy theorem one. Otherwise, you're just not going to do on the test. And then conservation of energy, it takes practice. It takes looking at examples. And so that's why I recommended looking at examples last time. Make sure you're looking at conservation of energy examples. Make sure you're asking me questions. And do the practice. It's a different way of thinking than we're used to. The math itself isn't too bad from what I'm used to. At least with most students, they can handle the math. Not, if you're not there, you're not there. That's okay. But most students can handle the math for the most part. It's a different way of thinking. And so make sure you're doing this practice. You're asking me questions and yeah, and so on. With that, I am done with this video. Have a good day.